Okay, so I'm doing the cluster analysis. First, I'll do a few exploratory analysis here about the few variables. Let's see, I think it's under Explore, imported data. Okay, so by looking at the distribution, we'll see some problem here. Before doing any analysis, or maybe there's another way, there's a better way that the tutorial talks about. It's under variable. By selecting multiple variables, almost all of them, you do explore, and you can do the same thing. It automatically shows you the histogram here. So most of these things are fine. Shu, yeah, your teammate is trying to find you. Okay, one thing you need to look at is this average household size. This data set is a smaller version of Census Bureau data at the household level. But the variables that are included in this sample data set is mostly the regional information. So it's not down to the household level, but it's down to the region where the household lives. It's probably the neighborhood. And the task here is to cluster neighborhoods, basically. With a few variables, you can't do much, but the purpose is to sort of, use the simplicity to learn the method. Okay, average household size is, ranges between, or household size ranges between 1 and could be up to 20. What's your household size? 2. If you consider your parents, then 3. If you consider your own dogs,
then 4.
And pets, and turtles, lizard, then it might be a lot. But it can only go up. It don't go down too much, right? So things like below 1 would be a little strange, and these automatic histogram binning tool, they sometimes are not intuitive. It looks at the range and use a default binning tool if there's no other problem, but it doesn't provide much help here. Here, you see a potential problem of 0 household size, but you're not sure because of the ranges, the binning method. So you can do a little adjustment here about the binning and be more sure about what does that bin cover. So is it really 0 or is it 0.4? It's hard to see. So you can do 2 things typically. Here you may only do 1 thing, but let's try. I'll try to have 1 bin per range of 1 to see if the 0 can be singled out. First of all, you see nothing here by the side, so there's no missing values here. If there's a missing value, they will show up as a big spike. There's no missing value, but there are quite a good, maybe 10%, very low number here, maybe 0.2 or maybe 0. I want to make sure if it's 0, I want to exclude it. But if it's not so small, maybe I want to retain it. So what you can do is to refine the binning method. It's all under graph property. Let's see. Currently, the number of bin is 9. I see the range is probably up to 5, so maybe I want 6 bins so that 0 value can be singled out, maybe. So I'll choose 6 bins and let's see. and you don't have to pick from the list. You can customize. So 6 beans it's not very helpful. Maybe 5 beans. It's almost, but it's definitely under 1. But you know, how small does it get? So the other alternative is to have many beans, like the tutorial says. Have many beans, you can at least, you know, finally you're able to single it out between 0 and 0.05. It's very small, close to 0, and there's a huge gap if you look very closely. There's a gap between them. So this spike of data can be considered, you know, has errors. You can safely exclude it at this point. So the filter tool can be useful in this case, and it's using a cutoff point, so it makes it easier to filter. Other than this variable, you can see some missing values here. All the households that has average close to 0 head count also has missing values on density. So sort of corroborates the theory that these data points might be problematic, maybe because of data conversion or data transfer, that some data are lost, or some other noisy data are introduced, which probably you can delete them. Right. So that's it. So to filter these, the next step is to use filter. It's under sample, filter. The filter tool is to exclude certain observations, rows of the data set that meet some criteria. And it has a default method for the class variable and for interval variable differently, because you know there are different ways to different methods for the two types. We don't have any class variable here, so it's not relevant. But typically, it calculates each of the unique level of the variable, the class variable, and calculate the percentage of cases that take that value. If the percentage is too slow, that means that case is very rare. And for the sake of exploratory analysis, you probably really don't care about a few rare cases. You know, the purpose is to get the big picture, is to lower the uncertainty. Knowing more about those rare cases don't reduce your uncertainty too much. You know, the idea is the focus is on big picture. So you can safely, you know, exclude them for most of the early stage projects. For interval variables, there are multiple ways to define extremity. You know, you can use standard deviation to sort of standardize the distance from the typical value, and you can specify a very specific value for each of the individual variables. In this case, that's what we do. We will not use a blanket uniform method of, like, say, standard deviation, but we will use user-specified limits, but only specify for those values that we want to filter on. So in this case, it's the average household head count. And selecting that, let's see, this is, I think, right. only want to do the household size. Filter method is the user specified, and according to the tutorial it's 0.1, but anything between 0.05 and 0.1 will do the job because that's where the gap is. So you can do 0.08 or 0.1, don't matter very much.
Did you run it, Dr. Mo?
No, not yet. I went into interval variables, interval variable ellipse. Right, filter lower limit. We didn't want to filter upper limit, it's only lower limit. And that's it. And after that you can run and look at the results.
What did you put as upper limit?
No, nothing. So dot. Keep it as the same.
You just put like the mean user defined and just leave it, or
I selected from the drop down menu as user specified.
yeah.
Yeah.
And
That for only that variable.
Yeah, and for that variable there was no upper limit or lower limit. Or just
I selected lower limit to be filtered. So let me show you. Wait,
okay,
what did I do?
0.1.
Why? Wait. I think I did this, right? Yeah. So yeah, I did this.
So 0.1.
0.1, yeah.
Okay.
And change this to user specified. If you don't change this, even if you specify some value, it won't take effect. Right? The two have to go together. All right. The results should confirm the action. Filtering by mean household size. By using a minimum of 0.1. Let's see how many rows are excluded. Let's see.
1081.
I have the same.
1081. Yeah, it's 3%. It's a very small, or quite small percentage. You can safely exclude them. All right, so you can of course use filter to deal with other variables. That's for a deeper dive. And for now, we'll move on to next stage. Next stage will be the clustering tool, and we'll only use a partial list of the variables. So we'll select to use those and not use the others. It will be under Explore, k-means. Does it say simply cluster? And it is the k-means cluster tool. So with this, and I'll talk about that in the slides in a little bit, you need to specify an upper limit of number of clusters. The program will try to figure out within that limit what might be the best number to pick, and it'll give you more options down the road. But it won't go beyond that limit. And there's one more important thing I need to talk about: the upper limit. Final. Wait, let's see. I think that's it. Final maximum number of the maximum number of clusters acceptable. For now, let's use something small. 3, which might be too small, but for the data set, and considering the situation, it's a household regions of the U.S. It's a representative sample, 33,000 cases. It's a large sample. 3 clusters may not be adequate, but we'll use that to do the exploration and see why it may be not adequate. One important preparation for the data set is, remember in K nearest neighbors, I talked about standardization, and it's very critical to do that. Standardization helps limit the impact of some arbitrary scales of the variables and make sure that the variable scale don't influence the result too much, right? And you want to do that because you need to get the big picture, right? You don't, let's say for k-nearest neighbors, you want the variations in the variables that really make an impact, not the scale itself. And you want those influential variables to be influential despite that some of them might have very small scales, right? So, so you want to standardize them. And the point here is the same. You want to leverage the natural separations of the cases based on whatever variable that might be able to help you separate the cases. So you don't want the arbitrary scale to affect that result. So that's why you need standardization. And here, standardization is built in automatically. Same with the neural networks. Neural networks has a built-in standardization because it's so important that it doesn't want you to forget about it. So it's simply included and select standardization. But you can tweak between standardization and range and give you a slightly different solution. Won't differ too much, but give you a little bit more room to customize. For now, we can choose standardization mostly because it's we'll use interval variables mostly, so standardization will not make a difference. And we'll choose only a partial list of variables. So I think we'll take away the geo information as well as population. We'll only retain 3 variables in the middle. Change them to no, will not be used in the analysis. And then I think we're ready to run. Let me check. And yeah, standardization. And one more thing, after clustering the sample, you have an option to create one more variable to designate the segment number. So let's say I decided that we need 3 clusters, so each case will be assigned to one of the 3 clusters. And you could create this new variable to designate the cluster membership, and then potentially, if it does help you separate a lot, then potentially you can use it as a target variable to train a supervised model and then to predict a new case. So that's possible. So that is the transition between exploratory to more sort of predictive project space. You can do that transition. It doesn't happen that fast. It won't give you a perfect solution. There's a lot of deep dive going on before you can reach that decision, but that's possible. So I think there's a decision that you can tick cluster variable row is the new cluster variable, and what row do you want SAS to designate for that new variable downstream? Right, we can do segment profile, and with that segment profile, it needs a cluster row, and this variable will be assigned a cluster row here. But you can change it to be input if you change to be input, it will be used as an input, or target, it will be a target variable. We can run it. So I used how many? I used 3. I used 3, but I was given 4. Seems like, hold on, the solution picked 4. Final maximum. Minimum. There's minimum you can choose. Preliminary maximum. Well, let's see. Wait. So I was expecting 3 clusters, but I was given 4 still. You can see the proportion of cases under each cluster. Let's confirm if we have 4 clusters. Number of cluster 4 is 6. Cubic cluster. So to confirm the number of clusters, I need to go to the exported data set to look at the segment variable that's created. Browse. They're all 4 clusters, so probably there's an internal minimum. Maybe 4 is the internal minimum. It can't go below that. But you rarely will, with a large data set, you will rarely use 3 clusters. I picked 3 just to make sure I can make it simple when I explore the result. It seems like we'll be stuck with 4 clusters. But the question is, how do you pick the number of clusters? If you have a simple data set, which I will demonstrate when I demonstrate the process of the algorithm, I'll use a very simple data set, 8 points, 2 variables, which you can use a scatter plot to see very clearly how the points separate. And you can, humans are very good at that low dimensional visual separation. Humans are built for that. But how does computer deal with that very quickly, right? In that case, you can have a very small number of clusters, but with high dimensional data set, let's say 20 variables or maybe beyond that, you can't even see because you can't draw a graph with 20 variables. But then, what tools do you have to help you or guide you about the specific number to pick for k? One tool is called CCC. It's a cubic cluster. What? I think it's CCC. Well, let's see. I have it here. Scoring. Yeah. CCC plot. It shows you with this data set how the CCC statistic changes when you have different number of clusters based on the same algorithm. And it's a messy, confusing chart. You're supposed to look for a sudden increase along the line, but discard anything larger than 20 or something like that. So it can go wild, and you don't have to, because with 20 or even 30 clusters, it doesn't help too much. Because your point is to lower the uncertainty. With 20 clusters, it's hard to profile and have unique messages for each. I'll make the points smaller. But too small. Yeah. So it looks like a sudden increase, like a kink in the graph is number 4. Probably that's why it picks number 4 as a final solution. So this is one of the tools that can be helpful. Other tools you can rely on your knowledge, right? You may have a better knowledge about the domain problem, and you may have a preference for a number, or it's the bottom line marketing resources that you have. How many resources we have to profile different groups. We only have resources to profile 5 groups, and go with it. You have to honor what the statistics says. It's a very practical problem. Right. With the cluster, we can do some. We can do some exploratory analysis, which will be fun. Explore. Yes. Okay. So first thing, I make sure that I have the entire sample. So anytime you work with a sampling tool in SAS, make sure you always check the sampling method. So in this time, still didn't fetch everything, but fetched maximum 20,000 cases, and that's as much as it can get. With these 20,000 cases, let's look at the map and how does the cluster work. So this is a geo data set that has coordinates. So you can use coordinates to display. Scatter should be under. Scatter, the first one. Wow, it's hard to work. Okay. We'll use the X as X, Y as Y. Use the segment as group. I think that's it. To use different colors to show the segment, the clusters basically. Oh, we use color actually. Color code the segment, but we'll show the information that we use for clustering, the 3 variables, to show up in the tooltip. And yeah, good. You refer to this for specifics, and that's it. Okay, and you can modify the tiles. Okay.
I have a question.
Yeah.
When we pick tip, it only lets us choose one as tip.
Yeah.
Okay. There's a box underneath.
Oh, allow multiple roles, right? That's okay.
Yeah, mark it, and you can choose multiple. So it's color, but not groups. I think groups is maybe better because we have few groups. I like to do a different group, different chart.
Looks like states.
X, Y, Y, group, and select Yeah, this time we have distinct colors. Great. Okay. So oh, we have a red. What's this color?
Okay,
Like orange, blue, and green. Okay. So you can see large areas of Midwest. There are group 2 and median household income is one of the variables. Yeah, the large areas, except for pockets of areas, maybe large cities locally, they are quite homogeneous in the sense of the 3 variables that we used. Average household size, median household income of the region. You know, if you move around most of these, the household income, median household income between 23,000 and 27,000, as I see. It may go slightly beyond that. So group 2 may be the largest group that covers majority of the United States. But let's look at some of the minority segments. This one. This covers large areas of California. Household size. Region density tend to be higher. I think region density may play a big role here for large cities and more populated states. States that I see here is California, New Mexico, Texas, Florida, and northeastern, large areas of northeastern. That density percentile tend to be higher up, closer to 100 than the other, than to 0. What about here? Wait, no, this one is not very small. It's a 58, 56, 53. So more populated and more densely populated. Average household size may not be different that much. Income have medium differentiations between the clusters. And remember the connected graphs that you can use to select a segment and look at the percentage of that segment by select a slice of the data, and you can with this map, it's good to see the separation, but it's hard to see the local percentages because there are overlaps of the points, and this is one of the limitation of limitation of scatter plot. Because whenever there are densely overlapped points, you with different groups, you can't differentiate because there are overlaps. You can make a simple histogram of the segment. To leverage the connections of the points between the graphs. You have bigger map. Okay, the segment ID is really poorly scaled. We really should have. Yeah. scale is bad. Well, you know. This might work. So there are 4 groups, as you know. It's the largest group is the green. It's a green one. It's group 2. It covers almost everywhere. Group 1. Group 1 maybe even more highly populated than group 3. Group 3 covers those populated states, but group 1 almost concentrate on the big cities, it looks like. So with this slice, if I slice New York regions, I would imagine more of the group 1 and group 3 will be selected than the group 2 and 4. You know, you can see the population plays a density. Population density plays a big role here. Look at the Houston area. It's more evenly distributed. Los Angeles is maybe close to here. Yeah, it's hard to. Or you can zoom in. You zoom in. Yeah, but I don't see the map, so it's still hard to pinpoint where it is. But you can see a local separation here. So this group more segment 1. So you can do some. If you're familiar with the map, then it will be a better tool, more useful tool to you. Yeah. So with the exploration, you can do this. Seems like the 4 segments are at least somewhat meaningful in this context. You know, given that we know that much about the census and differences between states and cities. And what else can you do? So after you have the clusters, then typically in marketing campaigns, you need to look more closely at how each segment is different from the other segments or the larger population in terms of those variables that you use to cluster them, so that you can write a marketing campaign message, right? So it will be better to see the differences. The profile tool is something that you can use to help you differentiate the groups. With the exploration so far, it's hard to really write a precise message or anything close to precise to speak to that group. How do you speak to that group? Let's see which one is it? Utility. Where is the profile? Assess. Segment profile, yeah. And anything we have to do? Exclude those variables. Update. Let's see. So only use the variables plus a distance. So let's reject all of them and only select those that are useful. And also you need the segment and segment label. Wait, so yeah, these are default. I think that's right. Yeah. Make sure you have the same selection. Okay. And go ahead and run. So how useful is this tool? It uses the results produced by cluster. So you have all the information, cluster and membership, and it uses some graphing tools to. If you have more variables, then this graph will be kind of hard to read. It will have many charts. One chart is created for one variable that's used in clustering. I only use 3, so it's easier to see the graphs. If you have more variables, it can be harder to see. And the ordering is not perfect. It doesn't align the same variable on the same column, which make the tool a little bit hard to use further. But let's compare the same. Each row is a different segment. We have 4 segments here, and each column is a variable, but there might be different variables for different segments. Let's compare the density percentile. Density percentile assigns a number between 0 and 100 across the entire data set about where the density of this region lies in the entire sample, right? So a 0 value means of all the data points, this data has the lowest level of density. Has the sparsest population. If a value of 100 means densely populated city or region of this sample, right? So you have an equal representation of between 0 and 100, right? So segment 2 occupies the lower half. This boundary, this hollow histogram, is the entire sample. So that's why it's the same across the segments. But the colored bars are specific to this segment. So you can see a difference between the overall sample and this segment, right? The bars exceed the overall sample by double for this segment, for the lower areas of the population density percentile. That means segment 2 consists of those regions that are far less populated than, let's say, segment 3 and segment 1. Segment 3, on the other hand, has values of region density percentile that are mostly the upper half of the percentile variable, right? So segment 2 and 3 are the almost exact opposite of the majority of the U.S. regions, and these 2 segments are the dominant segments of this sample. Although their density are very different, these 2 segments have almost a very similar distribution and statistics on the household income, right? It mostly occupies, the mean coincides with the sample average, but it more occupies the lower segments of the population, or lower segments of the population income, as versus, this one is household income, actually. So segment 1 consists of those regions that have higher income than normal, much higher income. Doesn't even cover mean income for of the population. And population density of segment 1 is also, it occupies even higher portion of the percentile. For segment 4, household size is the last one. Okay. Anyway, for the average household size, the only distinctive segment would be segment 4 that consist of typically large households for this segment. You know, the mean of this segment is way more than the average of the entire population. But the other 3 segments have somewhat similar distributions and statistics on the average household size. So, you can think about ways to leverage the information that you see here. For a simplified problem, it's easier to work with the data that you see here, but it requires some matching and sorting out. But the comparison with the background distribution helps you in a way that you can differentiate a little bit about the segment on this particular variable, right? So this is how you can use it. I think there's a question in homework about differentiating and profiling each of the segment of the serial products. You will use the same serial data set. So you will use nutrition information that you see can differentiate this segment of cereal, and you'll use the difference to profile the segment. So that's it. Let's see. Let me stop the video.